Can it get any better? I've got my cupcake. It's Wednesday, and we got a Morse Code of Weather.
What's the face on it? Is it looking up at the clouds?
It's looking up at the clouds.
He's rolling his eyes.
Rolling his
Clumsy
eyes
you are.
at the forecast,
Yeah.
apparently.
Yeah.
Well, you know, last week we talked about multi-cell thunderstorms, and this week a little bit of a different take on single-cell thunderstorms. Jacob?
Yeah, so single-cell storms can be your garden variety, non-severe storms, but they can also lead to supercells that are discrete storms, single-cell storms that produce our most prolific severe weather. So these single-cell non-severe storms, Kevin mentioned this a couple minutes ago, pulse storms. In an environment where you have a decent amount of humidity and instability in the atmosphere with your daytime heating, you can get these small popcorn thunderstorms to develop across a region. So they're small, weak, short-lived, and form due to that daytime heating. The sun heats the ground heats the air, and we get enough convection or enough rising air to form these smaller thunderstorms with one updraft, one column of rising air, one downdraft, one column of sinking air with brief heavy rain or lightning. So our schematic here, they can last between 10 and 30 minutes or so before they fall apart, with some heavy rain and lightning in their most mature stage, and they can develop a gust front or outflow boundary as those rain-cooled air is descending, hitting the ground, and spreading out in all directions. So going step by step with these small pulse thunderstorms that are single cell, the cumulus cloud builds dominated by our updrafts. We have enough instability in the atmosphere in that one location. The cloud continues to grow into sometimes a cumulonimbus cloud. In that mature stage of development, we have both our updraft and our downdraft. With the downdraft, our sinking air, we can get a cold pool. We can get a little bit of that gust front with the rain and wind spreading out as it hits the ground. And then that storm will usually quickly dissipate as it becomes downdraft dominant. All of that air is sinking within the storm, and it falls apart. That cold air reaches the ground and spreads out in all directions, and our storm falls apart. On the other hand, supercell thunderstorms, again, discrete, usually single-cell storms, they're a lot more severe and cause our most prolific severe weather outbreaks. They're single rotating cells with a tilted updraft. Kind of looks like a corkscrew here, where you have rising winds within that big cumulonimbus cloud spinning around really quickly. They can last for several hours, producing tornadoes of very strong magnitudes, damaging winds, and large hail. On radar, these supercells usually have a bit of a hook echo appearance, with sometimes that tornado forming inside that hook echo. And again, these are discrete single-cell storms that can produce sometimes these large tornadoes within that hook on a radar image. And with multiple supercells that form in a certain area, sometimes the farther south one will be the strongest, as it has the most moisture available to it, usually coming up from the Gulf of Mexico, our moisture source. But there's a lot of complicated components to supercell thunderstorms that we'll get into in the next couple of minutes. It's all about, though, that rotating updraft within the center of the storm. And that is what allows it to sustain itself for several hours in some cases. It's highly organized with these updrafts and downdrafts that can contain up to 100-mile-per-hour plus winds, and that can lead to our severe weather and our damaging winds. And these are what usually produce our tornadoes. It's all because of shear, though, in the atmosphere. Shear needs to be present for these supercells to form. Shear is the changing of winds with direction or speed with height. So let's say we have a wind coming out of the south at 20 miles per hour, but aloft we have a wind coming in out of the east at 50 miles per hour. That is both directional and speed shear in the atmosphere, allowing for rotation to form and allowing for our updraft and our downdraft within these supercell thunderstorms to separate from each other. That allows the storm to not fall apart really quickly when we get the updraft to be separate from our downdraft. Another schematic here with some labels. We have our big cumulonimbus cloud. As it reaches a stable layer way up in the atmosphere, the cloud can't form anymore. We get an anvil. The cloud spreads out at that level of the atmosphere. We can sometimes get an overshooting top where the cloud tries to breach that stable layer of the atmosphere. But down near the ground is usually where all the action is, where we can get a wall cloud that descends. That's preceding a tornado usually, where we can have this lowered rotating cloud, and then a flanking line or some other cumulus clouds that form behind that main cumulonimbus cloud. These supercells can either be low precipitation, which is less common when there's not a whole lot of rain that falls along with our rotating cloud, or high precipitation, which is more common, and these can lead to rain-wrapped tornadoes, which are pretty dangerous because you can't see them. It's all about that rotating updraft inside the cloud, as I've mentioned. It's called the mesocyclone. That rotating updraft sustains our supercell thunderstorm, and it's that low pressure that sucks up all of our winds really high up into the cloud, creates for a more sustained environment for these supercells to track over longer distances. Within the storm, we have our updraft right near the center in the hook area of our storm on a radar appearance, but we also have those downdrafts. What has to rise in the atmosphere has to come down as well with that rain-cooled air. On the forward flank, or the frontward side of the storm, as you're envisioning this moving towards the north and east, that precipitation comes down and hits the ground and spreads out in all directions, but there's also a downdraft on the back side of the storm that can get wrapped around in that mesocyclone or in that rotating updraft. So some complicated components there as we're dissecting a supercell storm. And these can form tornadoes. When we get that updraft to be tilted in the atmosphere, we get a wall cloud that to descend a little bit closer to the ground, and then that tornado to come down and make contact with the ground. It's all formed with all of this rotation in the atmosphere. We have to have that downdraft or our winds and rain coming down and hitting the ground to form that rotation and form that really small-scale tornado on the bottom of some of these supercell thunderstorms. But even if it doesn't produce a tornado, these can produce our largest hailstones and our most damaging winds. So supercell, those discrete storms, when it's not connected to a big line or a big mass of thunderstorms, can sometimes be our most dangerous ones to watch out for.
That's so true.